Continuing with derivatives, and we're starting on page 9. Last time we talked about the alternative definition of the derivative and how we use that to check to see if a function was differentiable at a point. And remember, the slope coming from the left and coming from the right has to be the same. And so we're evaluating that rate of change from the left and the right. It has to be the same and it has to be continuous. Just because a function's continuous doesn't mean it's differentiable at every point. And we looked at some examples of that last time as well. So let's start on our notes. And we're just going to kind of go through some quick examples here. We're going to figure out where this thing is not continuous and explain why. Well, obviously, at x equals 6, so part A, x equals 6, this is not continuous. So we could say the limit, we would call this function, I guess, f of x. The limit of f of x, as we come from the left, as x goes to 6 from the left, is not equal to the limit as x goes to 6 from the right of f of x. And so that's really all there is to it. And that's the only spot where the function is not continuous. And now we want to find out where it's not differentiable. And there's kind of multiple different not places on here where it's not differentiable. The first one, right, looks like we have a sharp point right here. So not differentiable at x equals 3. And it's just a sharp turn. And that's all that is. When you get graphs like this, right, we're kind of looking at it, we've got sharp points. We also have a vertical tangent line right here. So maybe not necessarily a vertical, like you're thinking of a vertical tangent, but this line is vertical. And so essentially your tangent line would be vertical to this at this point, right? So right here at x equals 4, it just has that vertical tangent. Kind of following our way through, looks like here at x equals 5, we have another sharp point, or a sharp turn, right? Working our way through finally, we've got our x equals 6. That's also non-differentiable. It's because it's not continuous. So x equals 6, not continuous. Oops. Continuous. And then finally, we have this cusp, right? You could say sharp corner. We really want to identify what it is, and it's a cusp. So at x equals 8, we have a cusp. It's not too bad. We're going to go on and just think about our function here and kind of what's happening. So we want to know, like, at which labeled points is the slope of the graph 0. And so just think as we're following our graph, right? The slope, the rate of change, is 0. And now we're increasing. And we're going from an increasing slope, or a positive slope, we go to a negative slope. And so the rate of change is 0 there. So the rate of change is 0 at B and E. We want to know where the slope is positive. We can see A is definitely a negative slope. And then come around here, C is positive and D is positive. Those both have positive slopes. And then finally, we want to know where is the slope negative. Well, we already figured out A is negative. And then at F, we also have that negative slope at F. So A and F. That's it. Just looking at those slopes and thinking about the rate of change, right? What is it doing there? This is a pretty nice question, example 3. You're going to see some stuff like this on the AP exam, and you just kind of have to piece your way through it. And it seems like maybe it's a little bit strange at first. So it says this function f of, or let f be a function which satisfies the following. We have f of 2 plus h minus f of 2 is equal to this function for all real numbers h, and they want us to find f prime of 2. They want us to find the rate of change of 2. So the thing that you need to kind of recognize is this looks like the top part of our definition of the derivative. So that's kind of what we're going to do, right? We're looking for f prime of 2. And what this is, we're going to find this derivative, right? This is the limit as x goes to 2 of f of 2 plus h minus f of 2. We're using the definition, so it's all over h. Now, maybe like the sticky part at this point is like, what are you going to do with the rest of this? But remember, they're telling us that this is equal to this, so we can just do that substitution. So this becomes the limit as x goes to 2. And so here we've got our 5h minus 3h squared plus 9h cubed all over h. So we're just substituting these limit values in. And kind of looking at this, I realize that every term is divisible by h. So I'm just going to factor in h out. So we're going to have the limit as h. I'm sorry, this should have been an h, not an x. Pardon me. H. The limit as h goes to 0 of h times 5 minus 3h plus 9h squared all over h. My h is reduced, and when h goes to 0, right, just looking at this, we know that we're going to be left with, right, this h is going to become 0, and this h is going to become 0. We're just left with 5, and that's it. All right, continuing on, we're going to skip example 4. You guys can look at the notes and fill that out, and we're going to jump right to example 5. And so here's what it says. It says, given that the limit as x goes to 5 of f of x minus f of 5 over x minus 5 is equal to 3, which of the following must be true, might be true, or can never be true, and why? So we're going to have to do some justification. The thing that, like, you look at this, and you should recognize this, this is basically our alternate definition of the derivative, right? So this is essentially what we have here. We know this is our f of x, well, this is what we're finding. So f prime of 5 is equal to the limit as x approaches 5 of f of x minus f of 5 over x minus 5, and this is equal to 3. And so just remember, this is our derivative. This is basically our derivative here. We know it's equal to 3. I just added this f prime of 5 to kind of give us a visual. So it says f prime of 5 is equal to 3. Well, that must be true. That must be true because that is our definition of the derivative, our alternative. Definition of the derivative. Okay, so now they want to know, and that's it. We're just like matching this up. We know that this has to be true because they gave us this, and this is our alternative definition of the derivative. We have f prime of 5 is equal to 0. Well, we know that can't be true, so this is going to be never. And the justification is simply f prime of 5 is equal to 3. The definition, so from our definition, we know that this derivative at 5 is equal to 3. That's that rate of change. We want to know about, is f prime of 5 equal to 3? And so f prime of 5 might be equal to 3, but we don't know. So, and I think this is an important distinction with this might. This is like our IVT problems on the delta math. We don't have enough information to say it's never true or it must be true. We know that the function has to be continuous. We don't know what the function value at 5 is because remember, this that we found, that they give us is the rate of change at 5. We don't know what f of 5, the function value is 5 is, so we don't know what f of x is. We don't know what this function is. All we know is what the derivative is equal to. And then they say that for our next thing, f is continuous at x equals 0. This might be true. So it might be true, and for the same reason, we don't, f of x is unknown. Could be true. We can't say it isn't true. We can't say it must be true. We don't have enough information. It might be true. So f is continuous at x equals 5. So think about if does f need to be continuous at x equals 5? And if we go back to our derivative, think about what must be true to be able to take a derivative at a point. And this is one of our conditions to be able to take a derivative, right? This must be true. So because, and this is important, make sure you write this down, differentiation requires, whoops, not RI, excuse me, requires continuity. If it's not continuous at that point, you can't take a derivative at that point. And so finally we've got the limit as x goes to 5 of f of x equals f of 5. And so think about our 3 points, like the 3 things we need for continuity, right? The f of x, the function value has to exist, the derivative has to exist, and the function value and the derivative must be equal. So this is a must. This is the definition of continuity. And believe it or not, that is it for today. So once you're done with this, you put your notes away and you guys are going to start working on test corrections. Good luck.